So in lesson 3.2, our first vocabulary word we're going to talk about is relation. What's a relation? What's a relation? Patience. A set of ordered pairs. Any set of ordered pairs that's representing something is considered a relation. Okay, well, what's an ordered pair then? What's an ordered pair? We should have known that before we got to this lesson. Allison?
An ordered pair is like on a graph with 3, 2, and where the dot is.
Okay, so where we put the point on the coordinate plane, that ordered pair helps us know the location to go to. What's the first number represent in the ordered pair? The x value, and the second number in the ordered pair represents the y value. So anytime we have a set of ordered pairs, we can say it's a relation. Okay, well, a relation can be shown either as a group of ordered pairs, or if we want a even different kind of visual of it, we can make it into a table, a graph, or a mapping diagram. And we're going to practice making those on the last page of our notes. And then it says the domain is all the x values. We've got to know what domain means. Domain means the set of numbers that this relation allows x to be. And the range is all the y values. So the range is the set of numbers that all the y's can be from this relation. So a relation is a set of ordered pairs. We know that ordered pairs have x's and y's. We know that the domain is going to be made up of the x's. We know the range is going to be made up of the y's. So let's just practice finding the domain and the range. I am going to change a little bit about how they did this on here. When we list our domain and range, we're always going to do it in numerical order from least to greatest, okay? So in our first one here, this table that we have when x is equal to 3, what's y equal to? 1. When x is equal to 4, what's y? 2. When x is equal to 5, what's y? 2. So in reality here, we actually have 5 ordered pairs. This would be ordered pair 3, 1, wouldn't it? And then we have 3 other ordered pairs. So it is a relation, just written in table form. Well, the domain, we list any possible things, any possible values that x can be. Well, according to our table here, x can be 3, 4, 5, and 6. And they already have that one in numerical order. Notice how they write it, though. Capital D for domain. Curly little brackets like this for showing set, a set of numbers. And the set of numbers for this particular relation, the set of domain, is 3, 4, 5, and 6. Well, then the range comes along, and they want that too. So the range is this information, R, capital R for range, and nice little brackets to show the set of numbers again. But notice, what did they not do?
They did not list the 2 twice.
They did not list the 2 twice. We don't have. We're just showing what are all the possible values y can be. It can be 1, it can be 2, it can be 3. We don't have to say 2 twice. Okay. Well, that's when it's in a table. That's how we can locate so the domain is made up of all of the x values. The range, made up of all of the y values. Don't need to do any repeats in either of them. Well, what if it's in a mapping diagram? Does anybody know what number of the ordered pair is being represented in the first oval? The x. Just like we put the x first in the ordered pair, that first oval is really representing the x values. And this oval is representing the y values. Now, in this case, we could say that it has how many ordered pairs, this relation? How many ordered pairs does that relation have?
4.
4. Because when x is equal to 7, y is 3. It's being mapped to 3. When x is 5, y is 6. And they each only have one y value they're getting mapped to, don't they? So there's 4 ordered pairs here. So again, here's where we're going to change this up a little bit from the way they did it. When we do the domain and the range, we're going to put them in numerical order. So I want you to cross off this one. We're going to do it the way I want you to do it. I guess it gets to be my way. And we're going to list all of the possible x values in numerical order from least to greatest. So what are we going to start with? 0. What's the next one? 2, 5, 7. So we're just changing up the order, aren't we? So we're going to list the domain and the range in numerical order from least to greatest. And then do we need to rename the range? No. It gives us all the y values. They're already in numerical order from least to greatest, so we have a good range. Okay, anybody have questions about finding them when they're in a table or a mapping diagram? Those are actually the easier ones to find. But do you have any questions about it? I don't want to say easy and then you're like, I can't ask a question. Okay, well then let's go look at when they're in a graph. When they're in a graph, what kind of a graph is this? Is this a continuous or a discrete? That's discrete?
No, it's continuous.
That's continuous, isn't it? There aren't any breaks between points on this one. There is a endpoint at each end. We'll give you that. But this is a continuous graph. So when it is a continuous graph, do you think we can possibly list all of the ordered pairs that are on that line segment? What do you think? Do you think it's possible to list all of the ordered pairs, all the names of points that are on that line segment? No, because how many points are on that line segment? An infinite number of them. Too many for us to even start. So here's what we have to do. When we have a continuous graph, that we can't just say, oh, okay, there's this point and this point and this point, and here are their names, and now I know what my domain and range is. When we don't have that, we have to do them as a compound inequality. And notice it is the and compound inequality because it's between 2 points. So we're going to change this up a little bit, though. We're going to put some brackets around those, showing it's a set of numbers still, okay? But I want to know, how did they get those compound inequalities? So I'm thinking that maybe a good place to start would be to name those endpoints where that line stops, and that line segment stops at each end. So what's the ordered pair name of this point right here, at that end? What's its ordered pair name? Look on your papers. You can't see up here. You got the same paper. John?
2, 5.
2, 5. So this point right here is the one we're naming. 2, 5. That's a comma in between there. It looks kind of like a 1, but it's really a comma. Okay, 2, 5. And what's this endpoint's ordered pair name? 7, 3. Okay. So it's looking like the x values of all the points from one endpoint to the other lie somewhere between 2 and 7, right? So the x values, the domain, the smallest one is 2, the largest one is 7, and there's a whole bunch of other x values in between there, like crazy things like 3.1111111. There's all kinds of other x values. So we can't list them all, so we're going to write it as a compound inequality. 2 is the one endpoint, 7 is the other. X can be any number in between those. Same thing with the range. Let's look at the range. The range goes as high as 5 and as low as 3. Its endpoints are 3 and 5. Range, y values. So notice how they wrote it. 3 is at one end, 5 is at the other. It's in between those, and the equal to bar is included because the endpoints are also included, aren't they? So we're going to practice that. So let's just, anybody have a question about that at the moment though? They have these extra little, dash lines on there, and basically what they're doing is just kind of showing how to, determine the domain and range by counting. Okay, let's do some practice here. Number 1, we got a table. What would be our domain for this relation? Capital D, colon, set notation. Patience, what's our domain?
-2, -1, 0, 1.
Okay, actually get to put them down in the order they're in the table, don't we? All the x values make up the domain. Okay, what's our range for this one? What's our range for this one? Kenzie?
0, 1, and
0, 1, and 4. We don't need to list the 1 twice, even though it shows up twice, or I mean not the 1, the 4 twice, even though it shows up twice. And we put them in numerical order from least to greatest. So in other words, once they're in domain and range notation, we can't tell the ordered pairs anymore. We have to tell the ordered pairs from the table. How many ordered pairs are there in that relation?
4.
4. There are actually 4 ordered pairs, aren't there? Okay. Anybody got questions about that one? Okay, why don't you go ahead and try and do it from the ordered pair notation then. We have how many ordered pairs in number 2? 3. Okay, go ahead and write your domain and range for that relation. Try it on your own. What's the domain? What's the range? Okay, who wants to share their domain? Justine?
-5, -2, and 4.
Okay, -5 is the smallest, -2 and 4. Okay, those are all of the x values. Okay, Aubrey, how about the range?
5, 6, and 12.
5, 6, and 12 in least to greatest. Good job. Okay. How about number 3? Now it's a mapping diagram. We have to give the domain and range. How many ordered pairs are there in that one?
4.
4. Okay. Which oval represents the x's?
The one on the left.
The one on the left. The one on the left will always, because remember the one on the left in an ordered pair is always x. So that's going to be x, this is going to be y. What's our domain? What's our range? Okay. So what's our domain?
0, 1, 2, 3.
Okay, 0, 1, 2, 3. Okay, and what's our range? Kenzie?
5, 6, 7, and 8.
5, 6, 7, and 8. Okay. So notice what happens. When we put them in the domain and range, we can no longer tell their ordered pair relationship. Does 0 go with 5? No. So we can't write the ordered pairs from the domain and range set notation. We need to get it from either table notation, ordered pair notation, or graph. We could take it from a graph. Okay? How about the next mapping diagram? How many ordered pairs are there in that one? Dylan?
There's 4.
There's 4. And what, could you enlighten me how there can be 3 x values but 4 ordered pairs? Go ahead.
Well, -4 is for both 11 and 12.
Okay, so there's 2 ordered pairs involved there, aren't there? -4 and 11, and -4 and 12. So how do we write our domain for this then?
Same way it's written there.
Same way?
-5, -4, -3.
Yeah, we're gonna, so I hope you're starting to notice that however many members there are in the oval in the map, there's that many members in the domain. However many members there are in the oval for the range, there's that many members in the range for the set notation also. In other words, they don't do any repeating in a mapping diagram, just like we don't do any repeating in the domain and range, do we? So what's the range for this one?
10, 11, 12, and 13.
Yeah, all 4 of those, 10, 11, 12, and 13. Okay, now right now all we're learning is how to pick them up, but the domain and range play a very big role in all the mathematics you'll do from here on out. So we have to make sure that first of all we can identify it properly, and then we'll start talking eventually about what does that really mean, okay? So now we're going to do it from graphs. Let's look at number 5. What do you think the first thing we better do in that one is to help us out? Identify the what? the endpoints, right? Wouldn't that be useful? So we got an endpoint here and we got an endpoint here. Because it's a continuous graph, so are we going to be able to write the the numbers individually? If it's a continuous graph? No, we're going to have to use a compound inequality, aren't we? Yeah. So what's this one's ordered pair name?
-2, 1.
-2, 1. 2 to the left, 1 up. What's the other one's ordered pair name?
2, 4.
2, 4. Okay, now that we've identified the endpoints, you see if you can write the domain and the range for that graph, for that relation. How many ordered pairs does it have? Not just 2. An infinite number of them. Okay, who wants to offer up the domain? Nita?
-2 is less than or equal to x, and x is less than or equal to 2.
Oops, not a parenthesis, a nice fancy bracket. Okay, anybody want to disagree, agree? Thumbs up if you agree. Okay, yeah, that's it, that's the one. Okay, what's the range? Shelby?
X is greater than 1, which is 6, 1 is less than x, and x is less than 4.
So like that, did I write it the way you meant? Okay. Agree? Disagree? Oh, we got some disagreement going on, okay? Got some people agreeing and some people disagreeing, okay? Kenzie, what's up?
It should be less than or equal to.
Oh, we gotta have the equal to there because 1 and 4 should be included. Okay, what else? Nikki?
X should be 1.
X should be y. The range is made up of y values, and you'll make that mistake easily. Yeah, that range has to be made up of y values. So did everybody see how we get, first of all, these numbers? -2, +2, right? Those are the endpoints. And then we have, for the range, we have our y's are involved in the range, so 1 to 4. So 1 to 4, okay? Okay, well then, go ahead and try the next one now that you got this all figured out. Is this a continuous graph or discrete?
Looks continuous.
Okay, discrete means you can actually count the points.
It's continuous.
It's continuous. So, do you think you're going to have to write a compound inequality?
Multi-step compound.
A multi-step one? Oh, I don't think so.
No?
Anybody have a suggestion where to start? The points at the corners? Okay, let's do that. Let's start identifying the points on the corners. So what are the corner points? Let's see, what's this one?
-3.
Okay, -3, +3. What's this one?
-3, 1.
-3, 1. Okay, what's this one?
2, 3.
2, 3. Okay, and what's this one?
2, 1.
2, 1. Okay. Remember, the domain is all the possible x's, and the range is all the possible y's. So the domain is all the possible x's. X's go across. So how far can we go from here to here?
-3.
-3 to 2. Same up here, isn't it? Doesn't matter. There are no x's not included outside of those numbers, are there? So between -3 and +2. Okay? Kennedy, what's the range? John?
1 is less than or equal to x, which is less than or equal to 3.
Patience, what's the problem?
Needs to be a Y.
Needs
Oh,
to
yeah,
be a
Y.
Y. Okay. So anything else? Or can we is it thumbs up now? Okay. So again, Y's are the up and down. What's the lowest Y point? Y value on the point? 1. And what's the highest? 3. It's right here. Lowest is 1, highest is 3. Okay. Think you got an idea how to do the domain arrange from those darn graphs? Yeah? Okay. So if we have a continuous graph, we have to use a compound inequality. Okay. Here's where it gets tricky. Not all relations are functions. A function means that you have a type of relation where each x value, a domain value, can be paired with exactly one y value. In other words, in that relationship, each x has only one y. So if x is 3 and you got a y equal to 4, that's cool. If you have x is 3 and you got another time when x is 3 and y is equal to 5, that's a different y value. Now it's not a function. Each x can only have one y value. They can't be different y values. So in this one, notice, when x is 2, y is 3. When x is 3, y is 4. 4, 4. Oh, some of you are maybe right now saying, but wait a minute, there's 2 4s. But does the y control this situation or does the x? The x does. Each x can only have one y. Does x equal 3 only have one y? 4. Yeah. When x is 4, does it only have one y? Yeah, it's 4. I don't care if it's the same as the last y, but because it's a different x. It's the x's that have to be different, and they can have different y's. They can't have the same y, or then they can't have different y's, or they're not considered a function. In this case, they have the same y. That's okay. They're different x's. And here we have 5 and 6, all as well. So that's a function. Here just happens to be the graph of that table. And look at what happens on the graph. If there's going to be 2 different y values, there'd be another point somewhere along the way here. Somewhere along the way, when x is equal to 2, if there was another y value, there'd be another point. But there's not. There's only one point where x is equal to 2. There's only one point where x is equal to 3. There's only one point where x is equal to 4. And there's only one point where x is equal to 5. So the graph shows it by that there's no points lined up above or below any of these. Okay? So that shows a function. And then how could we tell from a mapping diagram? Well, we look at it and we say, when x is 2, y is 4. When x is 7, y is 4. Doesn't matter though, when x is 7, it still only has one y value. In other words, when x is 2, are there 2 arrows going out from it? When x is 2, are there 2 arrows going out from it? No. When x is 2, it's only going to the 4, isn't it? So this is ordered pair 2, 4. What's this? What's this ordered pair? 7, 4. Yeah, wake him up, Nicholas. Thank you. And what's another ordered pair? 8, 6. And what's another ordered pair? 15, 12. Are there any more? No. Do we have any repeat x values? No. Each x value has only one y value. Each x value has only one y value. Because notice what happens over here in this mapping diagram. This is ordered pair negative 4, 3. This is ordered pair negative 5, 4. This is ordered pair negative 6, 7. This is ordered pair negative 6, 10. Is there a problem here? Yeah. When x is equal to negative 6, we have two different y values. So that one's not a function. And notice what happens on a graph when it's not a function. Right here, here's the problem. When x is equal to 3, we have 3, 4, and we have 3, 6. That's a problem. Two different y values. And where's the problem in our table? When x is 6, it has a 2 for a y and a 3 for a y. Can it have that and be a function? No. So these are the ones that are hardest to wrap your head around and decide when is it a function or not. Because not all relations are functions. Okay, so let's go on and practice that. Number 7. What do you think? That table of ordered pairs that is a relation represent a function? Yes or no?
I say no.
No, why not?
Because the negative 3's repeat in the x.
Yeah, when you have x equals negative 3, you got 2 and 3, so we're going to say not a function. And it says explain. We're going to say when x equals negative 3 in sentence form. When x equals negative 3, there are, some of you are not writing, two different y values. So when they tell you to explain, you're going to write a sentence that explains why you are answering that it is or it is not. Question about that one? Okay, let's look at number 8. What do you think? Is it a function?
Yes.
Okay. Why?
Because all the x's are different.
Okay. All the x's are different. That'd be, kind of one way to think of it. There's not an x value ever repeated, so if it's not repeated, it can't have another y value, right? So we could say it's a function because for each x value, there is only one y value. For each x value, there is only one y value. And a really quick way to tell that is you look and you see, are the x's ever repeated? And they're not. So if they're not ever repeated, they can't have more than one y value, can they? Okay, how about number 9?
Yes.
It is a function?
Yes.
Okay, because?
The x's don't repeat. They're all different.
No, it's not.
Can I pick a spot here like, oh, but how about right here at the top of the triangle and then right here on the bottom of the triangle? Huh. What's this one's ordered pair name?
3, 3.
3, 3. What's this one's ordered pair name?
3, negative 1.
When x is equal to 3, we get two different y values, don't we? In fact, I bet there's a whole bunch of times on this I can make that happen, can I? Could I go over here and say, okay, I want this one and this one. Are there two different y values for the same x value? Yeah. I could come over here and do this one and this one. Are there two different y values for the same x value? Yeah. There's a whole bunch of places that it is. So we're going to say not a function. Several x values, more than we can name, several x values have two different y values. Several of them do. We could go on all day trying to find them. So that's not a function. Remember, when 2 points line up above or below each other, they share the same x value. It just became a relation that's not a function. Okay, let's go on. We got about 10 minutes to finish up here, and we got more to do. Okay, express each relation as a table, as a graph, and as a mapping diagram. So when it's in a table, the x and y's need to stay together. Delon. So in a table, and we're going to put the x values in numerical order from least to greatest. So do that first. List your x values in numerical order from least to greatest. But then make sure you go and put the appropriate y value with them. The y values won't be in numerical order. Only the x's will be. So when x is equal to -2, y is 5. When x is equal to -1, y is 1. The other time when x is equal to -1, we got a -2 for y. And when x is 3, we have a 1 for y. Okay, now we're going to graph those points. So graph them. Put all those ordered pairs, all those points on your graph. Oops, not there. And hopefully you're starting to notice, they're not asking us this one, but is this one a function? No. When x is equal to -1, we have two different y values, don't we? Okay. In a mapping diagram, that's like, it's kind of like the same as in a domain. In a mapping diagram, remember the first one is your x's, this is your y's. You put the x's in numerical order, you do not repeat them. So we have -2, -1, and 3. Don't repeat that, -1. And then we go to the y's, and we're going to put those in. Remember, in the mapping diagram, they're in numerical order, though. So we're going to go -2, and then 1, and then 5. So -2 is the smallest in the y column. 1 is the next, and 5. We don't need to repeat the 1. And now we're going to draw nice arrows, mapping the x values to their appropriate y value. So -2 has to be mapped to 5. -1 has to be mapped to +1 and to -2. And 3 has to be mapped to 1. Mapping diagrams can get sometimes be kind of messy. So you got to try and be as neat as you possibly can. Anybody get questions on it? Okay. Remember numerical order. 1, 2, 3, 4, 5. So we're reversing them. 1, 2, 3, 4, 5. Okay. They all have a y value of 3. Go ahead and graph those. Should be pretty easy. They should line up in a horizontal pattern, shouldn't they? Is that a function? What do you think? Does each x value have only one y value? Yeah. Okay. Remember, this is our mapping diagram. In our mapping diagram, we list them in numerical order from least to greatest, and we never repeat a number. So what's this one going to look like?
1, 2, 3, 4, 5.
1, 2, 3, 4, 5.
3.
3. And each of them get mapped to it, don't they? Okay. So that was practicing making tables, graphs, mapping diagrams. Any questions? Okay, now we're going to practice finding the domain and range of each relation and deciding if it's a function or not. We're going to kind of pull together what we did on that first page. Okay, what's the domain in this one?
0, 1, 2, 3, 4.
Oh, careful, is this discrete?
No.
It's continuous. So we need an endpoint and an endpoint. Oh yeah. So this is what?
0, 0.
0, 0. And this is?
4, 4.
4, 4. So the domain is
0 is less than or equal to x, which is less than or equal to 4.
Okay, so, let's see, I keep doing that, I don't want a parenthesis there, I want all those fancy brackets, okay? So in other words, what's the smallest x value to the largest x value? And what's our range?
Less than or equal to y, which is
Is
less than
1, good job, yeah. And again, so this time, smallest y value, largest y value. Is this a function?
Yes.
Yeah.
Yes. Because there's several points on here. There's a whole bunch of points on here. But does the x value ever get repeated? No, it never gets repeated. So we would say it is a function. We would say each x value in that domain from 0 through 4 has exactly one y value. And that y value comes from the range 0 through 4. Okay, what's the domain for number 4? 8 and 9. Remember the mapping diagram kind of shows it to you, doesn't it? Okay. And then what's the range?
-9, -6,
-9, -6, -4.
and
And we're going to make our mapping diagrams the same way we do their mapping diagram. Their y's are turned around. They should be the other way, smallest to largest. Okay, function, yes or no? No. Oh, how come?
Because each x value has more than one y value.
Yeah, each x value has more than one y value. Oops, I kind of ran over into my other territory over here, so I better. More than one y value. When x is 8, it has 2 y values. Actually it has 3 y values, doesn't it? And when x is 9, it has 2 y values. Okay. Domain of this last one, number 5. What's its domain?
0, 1, 2.
0, 1, 2. What's its range?
4, 5, 6, 7, 8.
Yeah, now we're going to list all of those, because none of those were repeated, were they? Okay, is it a function? Why not?
Because one has 2 different y values, comes 2 and 2.
Oh. And 2 has 2 different y values. Okay, so we're going to say no when x equals 2 and x equals 1. Each has 2 different y values. This is going to be one of the hardest things to get a grasp on. When is it a function and when is it not? We got to make sure every time we explain it, we find it in our heads, okay?